Right now, out in the Egyptian desert, there is a tower glowing so brightly with like 1,000-degree heat that it honestly looks like a second sun has been tethered to the ground.
It's a wild thing to see, isn't it?
Oh, totally. And the craziest part about it, plant operators are going to use that exact same desert sunlight to power a city at midnight.
Yeah, which is just a massive shift in how we approach infrastructure.
Exactly. So today we're taking a deep dive into the engineering marvel that makes this all possible. Concentrating solar power, or CSP.
Right, and we're reviewing this fascinating stack of engineering studies and technical manuals today to really break down the mechanics behind these artificial suns.
Because, you know, if you're listening to this and you're looking at the dark blue solar panels on your neighbor's roof, you might be wondering, well, why don't we just build millions more of those and pair them with bigger batteries?
Which is a fair question.
Right. So our mission today is to unpack exactly why capturing solar heat instead of solar light changes the entire energy game.
We're going to explore the historical roots of this technology, the towering sci-fi-looking machines capturing the sun today,
And why the global solar belt, specifically Egypt, is serving as the ultimate testing ground for this whole deployment.
yeah. But to really understand where this thermal technology is going, I think we should look at the physics of how it started. I mean, the fundamental idea of harnessing solar heat is a totally ancient ambition.
Oh, yeah. The timeline and the sources goes all the way back to ancient Greece. Archimedes famously theorized using highly polished shields to concentrate sunlight and burn enemy ships.
Right, the death ray.
Yeah, the death ray.
Okay.
Whether or not he actually pulled it off is, a debate for historians.
Yeah.
But the underlying physics of light concentration, that was completely sound.
And that same physics just percolated for centuries. By the 18th century, you had the French naturalist Count de Buffon experimenting with multi-mirror setups.
Oh, wow, really?
Yeah, he angled multiple flat mirrors to hit a single focal point, and he successfully proved he could ignite wood from hundreds of feet away.
Which is essentially just the magnifying glass trick, right? I mean, if you've
Yeah.
ever spent a summer afternoon on the sidewalk trying to focus a beam of sunlight to burn a dry leaf, you totally understand the mechanism here.
Exactly. You take diffuse energy, sunlight spread over a large area, and you force it into a very small, highly energetic point.
So Buffon and the engineers who followed, they were just scaling up that childhood experiment to industrial proportions.
Pretty much. But the real leap from like a neat optical experiment to actual industrial application happened much later in 1913.
Right, with Frank Schumann.
Yes, Frank Schumann built this massive array of parabolic reflectors in Mahdi, Egypt.
It's just wild to think about. Over a century ago, this engineer was out in the Egyptian desert building sun-tracking mirrors.
But he wasn't trying to generate electricity because the power grid didn't really exist in a way that required it back then.
Right, so what was he doing with all that heat?
He was actually boiling water to create steam to drive heavy mechanical pumps for agricultural irrigation from the Nile River.
Wow. So he basically proved that concentrated solar heat could perform heavy, continuous industrial work.
Exactly. He laid the groundwork.
But, Schumann was pumping water, whereas today, you and I need to power laptops, hospitals, air conditioners. We run on electricity.
We do. Which brings us to the core difference between the CST technology we're discussing today and the photovoltaic or PV panels that most of us are familiar with.
Right, the ones on our roofs.
Yeah, the PV panels you see on residential roofs operate on a direct conversion principle. Photons from the sun hit a semiconductor material, usually silicon, and they physically knock electrons loose.
And that flow of electrons creates a direct electrical current.
Exactly. It's a very elegant, solid-state system. There are no moving parts.
But the glaring limitation there is that it only works when the sun is actively hitting the silicon, right?
Yes, a cloud rolls over or the sun goes down, and your generation just plummets to zero.
Which means, to get power at night with PV, a grid requires massive chemical batteries,
Right.
like lithium-ion banks.
And those are incredibly expensive and just super resource intensive to build at utility scale. So CSP takes a completely different indirect approach.
Right.
It doesn't convert sunlight into electricity at all. It converts sunlight into intense heat.
Wait, so let me get this straight. A CSP plant is essentially just a traditional fossil fuel power plant, but instead of burning coal or natural gas to boil the water, We're using a giant solar magnifying glass.
That is exactly it. The power block of a CSP plant is practically identical to a conventional thermal power plant.
That's fascinating.
You've got the same steam turbines, the same generators, the same cooling towers, and the whole advantage of going through this extra step creating heat instead of directly making electricity is thermal energy storage, or TES.
Because storing electricity in a chemical battery is difficult and expensive, but storing heat in a giant insulated thermos is much easier.
Yes, exactly. And when these mirror systems focus sunlight, they aren't usually heating water directly. They heat what's called a heat transfer fluid.
Right, the HTF. The technical manuals we read detail synthetic thermal oils for lower temperatures, and then for the high-end applications they use molten salts,
Yeah, the molten salts are wild. It's usually a mixture of sodium nitrate and potassium nitrate.
which sounds like fertilizer.
It basically is. At room temperature, it looks just like normal solid white powder, but heat it above a couple of 100 degrees Celsius, and it melts into this clear, flowing liquid.
Oh, wow.
It behaves dynamically, almost like water, but it can hold a massive amount of thermal energy without boiling into a gas.
Okay, but that sounds like an absolute engineering nightmare to manage. I mean, if it's a solid powder at room temperature, how do engineers keep it flowing through miles of pipes without it just freezing solid and destroying the entire plant's plumbing?
That is honestly one of the biggest operational challenges of a molten salt plant. The entire pipe network must be heavily insulated.
I would imagine.
And it has to be equipped with heat tracing, which is essentially just electric heater cables wrapped right around the pipes.
Wait, so the plant has to use its own electricity just to keep the salt liquid?
Yes, it's known as a parasitic load. They have to expend energy just to ensure the circulating salt never drops below around 250 degrees Celsius.
Okay, so assuming the plant successfully maintains that temperature, how does the actual storage cycle work?
It relies on a two-tank system. You start with a cold tank.
Right. And cold in this context means what? Liquid salt sitting at roughly 290 degrees Celsius.
Exactly. Cold is relative here. So during the day, massive pumps push that cold salt up to the solar receivers where it gets blasted by concentrated sunlight, and it jumps to around 560 degrees Celsius.
That is incredibly hot.
It is, and then it flows down into a heavily insulated hot tank.
And it just sits there.
Yep, it just sits there, retaining its heat with minimal loss until the grid needs it.
So when the sun sets and everyone gets home from work and turns on their appliances, demand obviously spikes.
Right, the evening peak.
The operators pull that 560-degree salt out of the hot tank, run it through a heat exchanger to boil water into high-pressure steam, spin the turbine, and put electricity on the grid in the pitch black.
Exactly. And this fundamentally shifts how a solar plant can operate. It allows CSP to function as a baseload plant, providing a steady, continuous stream of power around the clock.
Which PD just can't do without huge batteries.
Right. Or it can act as an intermediate load plant. Or, crucially, as a peak load plant, dumping electricity into the grid exactly when demand peaks in those evening hours.
We are literally decoupling the moment energy is generated from the moment it is consumed. It's brilliant.
It really is.
So let's look at the actual geometry of the machines doing this, because the industry leans heavily on two main designs for focusing light along a straight line.
Yeah.
And from what I read, these are the most commercially mature systems right now.
Right, the line focusing systems. The parabolic trough is definitely the most common. Imagine a massive U-shaped curved mirror stretching for hundreds of meters. These troughs track the sun on a single axis, slowly tilting from east to west as the day progresses.
So if the trough is a giant mirrored half pipe, the receiver is basically a tube running right down the dead center of that half pipe along the focal line.
Exactly. The sunlight hits the curve and bounces back onto that central pipe. And the synthetic oil flowing through that tube gets heated to about 400 degrees Celsius.
But there are some downsides to that shape, right?
Definitely.
No.
The primary engineering hurdle with parabolic troughs is their physical shape. Because they are enormous and deeply curved, they catch the wind like boat sails.
Oh, I didn't even think about the wind.
Yeah, so they require massive, heavy, rigid steel frames just to prevent them from twisting or warping in the wind. And obviously that drives up the cost of construction and continuous maintenance.
Which completely opens the door for the second line focusing technology, linear Fresnel reflectors.
Yes.
And this is named after Augustin Jean Fresnel, the physicist who invented those step lenses for lighthouses, right?
That's the guy. And a Fresnel system completely ditches the giant curved half pipe.
Okay, so what does it use instead?
It relies on long strips of flat mirrors.
Oh, okay. So if a parabolic trough is like a giant half pipe, the linear Fresnel is like taking that half pipe, shattering it into dozens of long, narrow, flat strips, and laying them flat on the ground.
That's a great way to picture it. You angle each individual strip just a tiny bit so they all bounce their light straight up to hit a stationary receiver pipe suspended directly above them.
So you achieve the exact same concentrated line of heat, but the hardware profile is entirely different.
Much different. Because the mirrors are flat and mounted very close to the ground, the wind profile is minimal. You don't need those massive steel support structures.
Wow.
They're significantly lighter, cheaper to manufacture, and much easier for cleaning crews to access.
Okay, but there has to be a trade-off. If they're cheaper and use less steel, why isn't every solar developer just building Fresnels instead of troughs?
It mostly comes down to optical efficiency. With a Fresnel system, because the mirrors are flat and laid out right next to each other on the ground, developers run into issues like shading and blocking.
What does that mean in practice?
Well, early in the morning or late in the afternoon, when the sun is low, one row of mirrors might cast a physical shadow on the row next to it. Or the light bouncing off one mirror might actually get blocked by the back of an adjacent mirror before it even reaches the receiver tube.
Oh, that makes sense. You're losing photons before they even hit the pipe.
Exactly. And there's also the issue of cosine losses. From the perspective of the incoming sunlight, an angled flat mirror effectively presents a smaller surface area than a mirror facing it head-on, so it just captures fewer total photons.
Whereas troughs, being one continuous curve that's always pointed directly at the sun, they capture more light per square meter, even if they are way more expensive to build.
Exactly. But it's worth noting that both of those line focusing systems generally top out around 400 degrees Celsius.
Right. And in the power generation world, running a steam turbine at 400 degrees is leaving a significant amount of efficiency on the table.
It really is.
This goes back to the laws of thermodynamics. Without getting bogged down in, like, the complex math of Carnot efficiency limits, the fundamental rule is pretty simple.
Yeah.
The greater the temperature difference between your heat source, so the steam in your cooling tower, the more mechanical work you could extract from the system.
Yes. Hotter steam means higher pressure, which means the turbine spins faster and generates more electricity from the exact same amount of fluid.
So to push past 400 degrees, engineers have to change the geometry entirely. We can't focus light along a long pipe anymore.
Right.
We have to focus it onto a single blistering point. And that brings us to the real powerhouses, solar towers.
These genuinely look like alien architecture.
They really do.
A solar tower system utilizes a tall central tower surrounded by a vast circular field of thousands of individual mirrors, and these mirrors are called heliostats.
And every single mirror in that massive field is mounted on a dual-axis tracker, meaning it can pivot up, down, left, and right independently right.
Exactly. A central computer commands all of these heliostats to track the sun across the sky, and it constantly adjusts their angle to reflect their specific beam of sunlight to one tiny target receiver at the very top of the central tower.
And when you have 10,000 mirrors bouncing the harsh desert sun onto a single point, the thermal energy is just staggering. Receiver temperatures routinely hit between 700 and 1,000 degrees Celsius.
And this is where the molten salt we discussed earlier becomes the true star of the show.
Oh, okay.
You pipe the 290-degree salt straight up the tower, run it through the receiver where it absorbs that 1,000-degree heat, and then you pipe it back down into the massive storage tanks at the base.
That's incredibly efficient for grid-scale storage.
It is. But there is actually a fourth technology in the literature that gets even hotter.
Oh, right, the parabolic dish.
Yes. These look pretty much identical to the giant satellite dishes you'd see at radio observatory, but the inside of the bowl is lined with perfectly curved mirrors.
And they track the sun on two axes, keeping the dish pointed directly at the sun all day long.
Right. And because of that perfect parabolic bowl shape, they don't suffer from the cosine losses or the shading issues of the linear system.
That's amazing.
The entire surface area of the dish is capturing and focusing light onto a single point suspended right in front of the dish.
The sources said they boast the highest concentration ratios in the entire industry, focusing up to 2,000 times the sun's normal intensity.
It's intense.
Yeah, the focal point can reach temperatures approaching 2,000 degrees Celsius.
And at those temperatures, you aren't piping molten salt or hot oil all the way up to that focal point and back down again.
Right, that would melt the pipes.
Probably.
Mm.
So instead, parabolic dishes usually mount a generator directly at the focal point. specifically a Stirling engine.
which is a fascinating piece of thermodynamics on its own.
Oh, absolutely.
Unlike the internal combustion engine in your car that burns gasoline inside the cylinder, a Stirling engine is an external combustion engine. It contains a permanently sealed gas, usually helium or hydrogen.
Right. The concentrated sunlight intensely heats the outside of the cylinder head. The gas inside gets extremely hot, expands rapidly, and pushes a piston.
And as the piston moves, it forces the gas into a cooler section of the engine where it contracts, pulling the piston back.
It's just a continuous rapid cycle of heating, expanding, cooling, and contracting to spin a generator. It's an incredibly elegant and highly efficient way to turn raw heat into electricity directly on the spot.
Okay, but I have a major logical pushback here.
Okay, let's hear it.
If the parabolic dish gets to 2,000 degrees, has the highest concentration ratio, and features the highest peak efficiency of converting solar energy to electricity, why do solar towers and parabolic troughs dominate the commercial market? I mean, why not just plant a million parabolic dishes in the desert?
It represents the ultimate engineering trade-off. Dishes are highly modular. If you need power for a remote mining operation or an off-grid village, you can drop a few dishes in, and they will generate power without needing a massive steam turbine or millions of gallons of cooling water.
Okay, that makes sense for remote stuff.
But for grid-scale power, they have a massive vulnerability: no thermal storage.
Oh, because they turn the heat into electricity instantly via that Stirling engine.
Exactly. There's no mechanism to trap that 2,000-degree heat for later use. The second the sun drops behind the horizon, the Stirling engine stops spinning and your generation hits zero.
Just like regular PV panels.
Right. Furthermore, consider the maintenance logistics. A large solar tower plant has one massive centralized steam turbine sitting on the ground.
Okay.
If you built a ditch plant with the exact same megawatt output, you might have 10,000 individual Stirling engines suspended 30 feet in the air.
Oh, wow. That sounds terrible.
It is. That's 10,000 engines that need seals replaced, moving parts lubricated, and constant mechanical oversight. The economics of maintenance heavily favor centralized systems like towers and troughs.
That is a fascinating trade-off. So we have this entire spectrum of technologies, from lower temp troughs to 1,000-degree molten salt towers. But you can't just drop a solar tower in London or Seattle and expect it to work, right?
Yeah.
The environmental requirements for CSP are incredibly strict.
Oh, absolutely. The raw energy is undeniably there globally. I mean, the Earth receives 174 petawatts of incoming solar radiation. Enough energy hits the planet in one single hour to power human civilization for an entire year.
Which is always a mind-blowing statistic.
It really is. But CSP relies entirely on a very specific metric called direct normal irradiance, or DNI.
So think of DNI as pure, unscattered sunbeams that hit you straight on. Like if you're standing outside on a slightly hazy day, the sunlight hits water vapor or dust in the air and it scatters. That scattered light is still bright. It can still hit a standard flat PV panel on your roof and generate some electricity. But scattered light goes in a million different directions. A mirror simply cannot catch scattered light and focus it cleanly onto a single point.
Exactly. CSP requires crisp, clear skies where the light beams travel straight from the sun to the mirror without hitting atmospheric interference.
So no heavy cloud cover, low humidity, and minimal atmospheric dust.
You need a dry, arid desert with relentless sun. And this physical constraint creates what engineers actually call the solar belt.
The solar belt.
Yeah, it's a geographical band mostly located between 15 and 40 degrees latitude north and south of the equator.
So we're talking about the American Southwest, the Atacama Desert in Chile, parts of Australia, and massive stretches of the Middle East and North Africa.
Yes. And the physical deployment data we reviewed really highlights Egypt as a uniquely strategic location for this exact infrastructure.
Which is awesome, because Egypt sits squarely in the sweet spot of the solar belt. The environmental data shows they enjoy an almost unparalleled 3,200 kilowatt hours of solar radiation per square meter annually.
That's massive.
Yeah, when you combine that intense irradiance with vast expanses of flat desert terrain, it's the perfect laboratory and deployment zone. The engineering studies detail several massive projects already proving the concept right, like the Kurimat plant.
Yeah, Kurimat is a brilliant piece of transitional engineering. It's a hybrid system.
How does that work?
It basically integrates 20 megawatts of parabolic trough solar technology directly into a conventional combined cycle natural gas plant.
Okay, so just as a quick refresher, a combined cycle gas plant normally burns natural gas to spin a primary gas turbine, and then captures the exhaust heat from that process to boil water and spin a secondary steam turbine.
Right. So at Kurimat, they pipe the steam generated by the solar trucks directly into that secondary steam turbine.
Oh, that's clever.
During the blazing heat of the day, the plant relies heavily on solar steam, burning far less natural gas.
Right.
But when the sun goes down, or if, say, a rare dust storm rolls in, operators can seamlessly increase the natural gas burn to keep the turbine spinning.
It guarantees stable, dispatchable power while drastically cutting fossil fuel consumption. That's a perfect stepping stone.
Exactly. And we also see smaller, more specialized deployments in Egypt, like the Borg El Arab project.
Yeah, which is a 1 megawatt plant using CSP heat, not just for electricity, but actually for water desalination.
Which is huge for arid region.
Absolutely.
Yeah.
And while it is heavily focused on traditional PV panels, the massive Benban solar park in Aswan highlights Egypt's broader, aggressive push into renewables. I read the country is targeting a 42% renewable energy mix by 2035.
The nations situated within the solar belt just possess this immense geographic advantage. They really have the physical potential to become the primary energy exporters of the 21st century.
Harnessing relentless solar radiation the exact same way oil-rich nations harness petroleum in the 20th century.
It's a total paradigm shift.
And honestly, it brings our entire deep dive full circle. Because think about it. In 1913, Frank Schumann was out in Maladi, Egypt, building his parabolic troughs. He clearly had the vision, but he was operating a century too early.
Way ahead of his time.
And today, that exact same blazing desert geography is being utilized to construct the next generation of global power infrastructure.
It really is a testament to iterative engineering. I mean, the progression from Archimedes' theoretical weapon to Buffon's burning glass, culminating in towering structures pumping 1,000-degree liquid salt.
It's amazing. We've looked at the sheer geometry of these machines today. The troughs and Fresnels focusing lines of light, the heliostats and dishes creating blinding points of energy.
Right.
But the real magic here isn't just catching the sun, it's the ability to trap its heat. Using synthetic oils and molten salts to literally bottle up the intensity of a high noon sun and release it seamlessly at midnight.
It removes the single greatest limitation of renewable energy.
It really does. So, I want to leave you, listening right now, with the concept to chew on. As these technologies scale, and as we construct these artificial suns in deserts around the world, we are looking at a future where the global energy grid is supported by colossal thermal batteries.
Yeah.
We are moving toward a reality where power generation is completely decoupled from the time of day. We are effectively making the very concept of nighttime obsolete for our energy needs.
That is a wild thought.
It really is. Keep that burning thought in mind the next time you step outside, look up, and feel the heat of the sun on your skin.